Welcome to Database Explained. In this video, we'll explore data storage and management systems. Databases are everywhere, from the apps on your phone to websites you visit daily. By the end of this video, you'll understand how databases work, why they're better than traditional file systems, and the key concepts that make them so powerful. Let's start by comparing traditional file systems with databases. In a file system, data is stored in separate files with lots of duplication. If the same customer name appears in multiple files, you have to update it everywhere. Databases solve this problem. They centralize data in one place, eliminating duplication. Databases also allow powerful queries to find information quickly, support multiple users working simultaneously, and have advanced security features. For complex data, databases are clearly the better choice. A database system has 6 main components working together. Hardware includes the physical servers and storage devices that hold your data. Software is the database management system itself, plus the operating system and network tools. Data is the actual information organized in tables. Procedures are the rules, guidelines, and security protocols that govern how data is managed. The query language, typically SQL, lets you ask questions about your data. Finally, users include database administrators, developers, and end users who interact with the system. There are several types of databases designed for different needs. Relational databases like MySQL and PostgreSQL organize data in tables with rows and columns, using SQL for queries. These are perfect for traditional business applications. NoSQL databases like MongoDB use flexible formats like JSON or key-value pairs, handling massive data volumes with changing structures. Hierarchical databases organize data in tree structures with parent-child relationships, useful for organizational hierarchies. Graph databases store data as nodes and relationships, excellent for social networks and recommendation systems. Database normalization is a process that organizes your data to reduce duplication and prevent problems. The goal is to eliminate redundant data, maintain consistency, prevent update errors, and improve query speed. There are 4 normal forms. First normal form means all data is atomic and has no repeating groups. Second normal form ensures everything depends on the primary key. Third normal form removes transitive dependencies. Boyce-Codd normal form is even stricter, requiring every determinant to be a key. Higher normal forms mean cleaner data, though they may require more tables. Databases enforce integrity constraints to ensure data quality. Domain constraints specify valid data types and ranges. For example, age must be an integer and cannot be negative. Entity constraints require unique primary keys that cannot be empty. This ensures each record is distinct. Referential constraints use foreign keys to maintain relationships between tables. A department ID in an employee's table must exist in the department's table. Key constraints enforce uniqueness, preventing duplicate email addresses or usernames. These rules work together to keep your data reliable. The ACID properties are fundamental to reliable databases. Atomicity means a transaction is all or nothing. If you transfer money between accounts, both the debit and credit happen, or neither happens. Consistency ensures the database stays valid before and after a transaction. After a money transfer, the total balance remains unchanged. Isolation prevents concurrent transactions from interfering with each other. If 2 people buy the last item simultaneously, only one succeeds. Durability guarantees committed data persists even after a system crash. Your booking confirmation stays in the system even if the server fails. Databases use isolation levels to control how transactions interact. At level 1, read uncommitted, transactions see uncommitted data from other transactions. This is the fastest, but allows dirty reads, non-repeatable reads, and phantom reads. Read committed only shows committed data, preventing dirty reads but allowing non-repeatable reads and phantom reads. This is the most common default level. Repeatable read guarantees the same data throughout your transaction, preventing dirty reads and non-repeatable reads, though phantom reads are possible. Serializable is the strictest level, executing transactions sequentially to prevent all anomalies, but it's the slowest. This table summarizes which problems each isolation level solves. Read uncommitted prevents none of the anomalies but has the highest performance. Read committed prevents dirty reads. Repeatable read prevents dirty reads and non-repeatable reads. Serializable prevents all three anomalies but sacrifices performance. The rule of thumb is simple. Start with the lowest isolation level that meets your application's needs. Higher isolation means greater data consistency, but lower concurrency and slower performance. Most applications run fine with read committed. How do you choose the right isolation level? Read committed is the default for most applications and provides a good balance. Use repeatable read for financial transactions and reporting where consistency is critical. Use serializable for high-stakes systems like auctions where only one winner is possible and race conditions could be catastrophic. Use read uncommitted only for analytical queries where approximate data is acceptable. Remember this key principle. Use the lowest isolation level that meets your consistency requirements. Higher isolation increases consistency but reduces concurrency. It's always better to start conservative with read committed, then upgrade only if testing reveals consistency problems. Let's see how these concepts apply in real scenarios. For analytics queries generating monthly sales reports, use read uncommitted. Approximate data is fine, and you prioritize speed. For inventory systems checking stock and processing orders, use read committed. It's the standard choice for most web applications and provides good concurrency. For money transfers between accounts, use repeatable read. You must see consistent balances throughout the transaction. Finally, for auction systems where only one person can win, use serializable. You're willing to accept slower processing because data integrity is critical. Each choice reflects a different balance between speed and reliability.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.